I think we can start. So now we have the pleasure to have Johan Samsing, and he will talk about measuring proper motion of gravitational wave sources with strong lensing.
Okay, thank you. So I really had a pleasure here talking with people here the last few days. I haven't worked for lensing for many years, so I was really trying to get up to speed, and it has been good to see what the people are working on and what kind of problems. So by looking at some of the other talks and generally what people are talking about here, I thought that I would start with discussing a little bit of astrophysics and actually also talking about what kind of cases that we are expecting to see, right? So because we can all cook up problems, and we think it's funny, to cook up these problems where you put binary black holes just next to supermassive black holes and see what happens. But if you ask people that are doing astrophysics, the probability for that to happen in the real nature is probably extremely close to zero. So even from the first 100 binary black hole mergers that we have been seeing, even the leading order estimates for how binary black holes form, is it in clusters, is in binary stars, we still have no idea, right? So even to leading order of these, we simply have no idea yet, right? So first I'm gonna go in and tell a little bit about what we expect, and I'm gonna show you some very interesting cases, because there are very, very interesting configurations that we for sure will see that are out there, right? And I will show you which one it is. And then during the last 10 minutes, I will go into this measuring of the relative motion of sources using strong lensing. So very briefly here first. So when we talk about gravitational wave sources, and we think about how do we disentangle these, right? This is basically what many of us are thinking about, also probing the field in between us and the source, right? That could be that we could split it up. That is what we normally do. We split it up in these categories. In this case, here I've been showing the dynamical formation of binary black holes versus binary stars. And we can already pinpoint a few different cases, even without specifying how exactly the binary black holes formed and so forth, because there is some differences just at the zeroth level. So when you go in and measure from the gravitational waveform, we measure the spin masses and eccentricity, as many of you know. And if you go to clusters, then, as I'm going to show you in a moment, the way that the binary black holes are pairing up is really through these chaotic scatterings. So the spins, very likely to be randomly orientated, where if you have binary stars, they're likely to be correlated with each other. The masses in the dense clusters, they also tend to be very close to each other, since that the masses in the clusters of the black holes, they tend to be larger than the stars. So the black holes, they segregate into the center, and it's typically black holes with similar mass that are interacting at any given time, where for binary stars, it could be basically anything, right? So for example, generating binary neutron stars or neutron stars with heavier black holes is extremely difficult in clusters. And I don't think, with 100,000 of cluster simulation and scatterings, maybe only a few so far has been seen on that level. And eccentricity can also be, formed in these very dense stellar systems, like through these chance encounters that I'm going to show you, where for binary stars it's not very likely. So this here was kind of the picture for many years, and we hope with LIGO within the first 100 mergers that we will have a very good picture. But as you know, we simply have no idea of how the mergers basically are distributing, even according to do this very rough cut here. So let me just make it even more difficult, and that kind of motivates like a lot of the work that all of us are doing. If we now go in and say, well, now let's say that we see an eccentric source. There's a lot of people working on the eccentric waveforms, right? Let us say that we see one of these sources. What are we going to learn? Well, if you are asking people that are doing galactic nuclei, they will definitely say, well, it's just a single capture in a galactic nuclear. That's what we said, 10 years ago. And the process is basically two black holes coming in. They undergo radiative capture, and then they merge. And then they can only merge in highly eccentric orbits. Otherwise, they wouldn't be able to be captured in the first place if the velocity dispersion is very high in the center. Right? It could also be people that are saying, well, we have been studying these binary stars for a lifetime, but we also thought about the case where there's a third object around. We have these quasi triples, and they can also create these eccentric mergers. And then there will be people like me that have been spending a lot of time these chaotic triple scatterings here and saying, well, I can calculate that about 5 to 10% of all mergers are through this channel, so I'm sure it's from this one here. So no matter what kind of things that we're going to observe, these eccentric mergers, or is a spin aligned, or this and that, we'll always have a subset of channels that we have to sit and disentangle. So now I'm going to show you, well, you can already, with some of your works, some of your ideas, tell the different channels apart. For example, over here, you don't have a third object around, right? So if you're thinking, oh, maybe if these two black holes are merging, I can see lensing from the third object. Well, now you can start to work out the probabilities. What are the lensing probabilities when I'm going to look for these and blah, 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 right? And the same case over here. Let us now take a look at some of the differences, the observable differences, and I will start with this one over here, right? And I will show you exactly how you can tell the differences, and that will, I hope, motivate a lot of the work that we are doing here and then give some new ideas, right? So if you're going to take at these very dense stellar clusters here, there are many different ways that the binary black holes can merge in them. You have these three-body mergers. I'll show them in a moment here that are labeled here. You have the two-body mergers. That's what we denote the mergers that are merging in between your scatterings. Right? So normally in clusters, you would have some binary here, and then the binary here is sitting and waiting for something else to happen. That could be like another black hole flying by here, but sometimes something is hitting, right? And then you undergo some triple scattering. That's what you call the three-body interaction that can result in the merger. It could also be that the eccentricity of my binary black hole being excited before it undergoes its next scattering. It merges before the next scattering, and then it merges. That's the two-body. And if the recoil of my triple scattering is so large that it's being kicked out of the cluster, that's the ejected mergers. Right? And we cannot simulate globular cluster systems, and we cannot simulate these very dense stellar systems in general. So we have to rely on calculating the scattering processes through these basically scattering experiments. So we can calculate probabilities and outcomes from these scatterings. Let me show you here a simulation on one of the scatterings here, and this is like a three-body scattering. These scatterings here happens all the time inside these dense stellar systems. You not just see it for black holes, you also see it for stars. You see the distribution of binaries, you see ejected binaries. The whole way that the cluster is sustained and is not, undergoing some kind of thermal collapse is through these scatterings, right? And the reason is that you form the binaries through random three-body motion inside the center, and the cluster all the time tries to contract, and it happens by the heavier black holes scattering out the lighter objects. Now you're going to see in a moment what happens here. So the third object is going to drive this binary here to very high centricity, so it's merging during the triple scattering. And this process here, if it's not being driven to a merger through this process here, it will result in that this third object will be kicked out, and the binary will be kicked also away from the center of mass and put some energy back into the cluster. Okay, so this generally is like a heat, like a battery for the cluster not to collapse. Yes, you have a question.
Yeah, this is a beautiful video. It's amazing.
Thank you. No, just a comment.
Now the question. If you just put these binaries in like in an original, the original configuration is kind of isotropic or something like this. How efficient is this process?
Okay, so let me just show you right here. So I just made a quick estimate here. Well, we have of course been calculating this to high detail in the papers that we wrote on this. But the idea basically here, okay, so I can argue that about 10% of all mergers in classical clusters are happening through this process. 10%. 10%. And people also found this through globular cluster simulators like Monte Carlo, right? So there's a very simple trick to calculate this. I'm just going to show you. Right? So if you have like three objects, two of them here, and you need some object here to undergo a merger, while you still have the binary of the third object bound here, you essentially just are going to compare energy scales, right? So if you have some object here that is coming in here and merging with this object here, and you start out with a Pearson center RP, then the radiated energy here is just coming from Peter's equations is m to the, these are these powers, I can't remember. Okay, like this. And then I have rp to the 7/2. This is just from Peter's equation. Right? So this is the energy loss over one parabolic passage. This is the characteristic energy loss. Where if I need a merger doing my triple scattering, then that here has to be comparable with the orbital binding energy, which is m squared over a. Right? So I can solve for what is the characteristic pericenter distance for the energy to be comparable with the orbital energy of my triple system. Right? So and then I get this equation a to the 2/7, m to the 5/7. Right? And I can calculate from the Newtonian case that if I have an isotropic scattering or if I have a binary, then the probability of creating a pericenter that's less than some value is proportional to that value divided by the semi-major axis. Okay. This is coming from the Newtonian case. This follows from there. This is the only thing that we need to use because now the probability that R is less than this one, given that's the same, the probability that I will generate a merger, right? Because if it's less than this characteristic value here, I will certainly merge because I will radiate more energy than my orbital. Right? I will end with a probability that is proportional to, I just put this in here, right? And the probability now goes as a to the minus 5/7, m to the 5/7. Now you can already see what this is basically because m is essentially my Schwarzschild radius, and if I write out for a single configuration of my binary up here, right, so this is the probability that one of these temporary binaries here are gonna merge. This one here is essentially just the Schwarzschild radius of one of my objects divided by the semi-major axis divided by 5 or to the power 5/7. And then the thing is that, so I can put in some numbers, right? And if I put in for 50 solar masses and 0.1 AU, which is characteristic distance globular clusters, I get 10 to the minus 4, 2 times 10 to the minus 4. That is probability that one of the binaries that are forming up here are merging while they're still bound to the single here. But as you can see here, you have many, many changes since you're trapped in this resonating state. So you basically have the number of chances that you're forming temporary binaries. So 1, 2, and on average, you can basically multiply this number here by 40 because you have this chaotic part here. So when you multiply these numbers here, and you weight with the number of black hole mergers from clusters, you will end at about 5 to 10% level. Right? Here you're already about 10 to the minus 2. So for a single scattering, there's about 1% chance that this will happen. But then you have many of these scatterings inside the cluster. So this thing here is happening very, very often, and we can very easily calculate exactly what is going on. Right? And it is part of the standard way of forming binary black hole mergers, because if it's not merging inside the cluster, this is a sketch from my friend Carl Rodriguez in one of his papers, right? You can see here, if you're starting out with 2 black holes up here, they will undergo hundreds of these scatterings. And sometimes you'll kick out the binary black hole here and then it will merge, but sometimes it is also merging inside the cluster doing one of these scatterings. And then one could go in and map, for example, okay, so what is the characteristic distribution in peak frequency of these 3-body scatterings? They are up here about, oh, now I lost the numbers here. But this is the LIGO band and this is the LISA band, right? So the one that are being kicked out moves into the LISA band, might have a small eccentricity, the same with the 2-body, where the 3-body mergers will show up in the LIGO with high eccentricity. So at this level, we can already say that we have an understanding of how clusters work. We can calculate the distribution of peak frequencies and eccentricities at different gravitational wave bands. But okay, that is okay, yeah? This here is the evolution of the peak frequency. So you start, and this here is the strain. So you're going here, and then you're going up here, and at some point the binary circularizes, and then it follows this traditional f to the minus 5/3 or whatever it is. Okay, but let us say that you now see some of these eccentric mergers that we know for sure are happening through this channel here, but it could also happen through some of the other channels. Well, just to get it more complicated, if I take and perform the same scatterings in an AGN disk, or like consider some kind of disk-like structure instead, the probability of forming these highly eccentric mergers grows from the cluster limit, 10 to the minus 3, up to about 10 to the minus 1. So you can boost the number of eccentric mergers by 2 orders of magnitude by just pushing the interactions inside a disk. So there's many ways that you can form these eccentric mergers. So how are we going to tell these apart from the rest of the population? Right? So the idea is to look at the modulation of this signal here as we are looking at the source. And that's the same idea as you're doing for binary pulsars. Right? So for the binary pulsars, you're looking for modulations in the pulses, and the same you can basically do here for the binary black holes. Right? And that's very close to what you were talking about yesterday. Right? You just look at the modulations to the gravitational waveform. And if you just go in and tap into all the literature that people have been doing on binary pulsars, you get everything for free. Here you just don't have a constant clock, you just have an inspiral, right? But your clock is your timing in between your waveforms or your wave cycles. This is one example here. This is the scattering that is happening inside a cluster, and then the observer is sitting down here and then seeing a displaced signal here, right? So this here is the unperturbed motion of my binary black hole. This is the merger, where this one here is the curved one. Okay. If I'm sitting down here as an observer, I see a time displacement as a function of time, which is basically just a measure of the curvature or the acceleration of the source. And that can map into a phase shift, so the time delay is down here. Now let's take a look at the properties of this phase shift and see if we can even measure it, right? So put it in another way, if you have this triple scattering here, right, then you have, in this case here, you have the assembly of my gravitational wave source here, and then the center of mass is still bound to the third object here, and then it's merging at some point here, and then let's say we sit as an observer out here, then let's think about all the different effects that we're going to see for this curvature and the effect from the third object. Now, we have built many ways of looking at this. Okay, so the one way is just to calculate to leading order what is the acceleration of the center of mass and so forth. But there are many other things that are taking place, right? So when you have binary black holes, also just sitting close to supermassive black holes, it is not just a binary that is just inspiraling by itself. There's tidal torques to it. The orbital plane is being torqued around, and all the small tidal effects are showing up sometimes to leading order in your perturbations to your gravitational wave signal. And many of the effects that we are talking about, the Doppler effects, say, right, that also that requires that you're looking at a specific angle, right, where all the tidal coupling terms, they are always visible, since it's the property of my binary motion that I'm just changing, and not like an observer-dependent property. So here, this is an example of some of the things that we have been building. This is the binary black hole that's merging around, in this case here, semi-supermassive black hole, 100 solar masses. I can choose whatever mass I want. And then once it's merging, I remove all my particles except the binary black hole, and then I simulate the system backwards. Okay, so this here is my clean inspiral, and this here is my perturbed inspiral. And now, so I just did it, in this case, in the post-Newtonian framework, so I can flip some signs and stuff like that, so I can simulate my binary backwards here. Now I can put an observer and I can see exactly what is the difference between the perturbed, the binary, and the unperturbed one here. And these here are some of the effects. Right, so up here, I'm showing the peak frequency of my unperturbed, that's the orange one, that goes here as a function of time leading up to merger, is growing, as you would expect, smoothly up here. But you see the modulations here in the perturbed one here, right? And the modulations here is due to a tidal coupling between the orbital precession of my binary and the tidal coupling relative to the object here, right? So as the binary precesses around, you have different tidal coupling. Sometimes it's pointing towards the heavy object, sometimes it's pointing the other way. And then I can also go in and calculate the phase shift. That is what you see down here. The red curve here is the Doppler term. So that's the Doppler term that you normally calculate that's proportional to the acceleration of my center of mass. But when I get earlier back in time here, I'm greatly dominated by tidal terms or tidal couplings to the binary. And well, this is an effect where I don't take into account the precision. There has been some papers where they're calculating these effects without the precision term, and you get completely wrong results. And the reason is that many of the tidal terms or tidal exchange of tidal energy that could happen in this system here are being averaged out as you have the strong precision of your binary here. Let me just show you some results here. Okay. So we can go in and calculate, let me see here, because I see I'm a little low on time. So if I, for example, have a binary black hole as I have here, the binary black hole moves around the single here. We have been able to go in and calculate exactly what is the phase shift that I showed you earlier, depending on the properties of this system here. So what I have up here is an equation, and it depends on the eccentricity of my binary as it spirals in, and it depends on the separation when the two objects merges here, or these two here, relative to the third object here. And then it depends on the initial pericenter distance here at capture. And then from this equation, I can just calculate what is the phase shift, the maximum phase shift that I will get. And now we did a lot of scatterings, the student and I, Kai Hendricks from the Niels Bohr Institute. We did a few 100,000 scatterings. And then with this formalism here, we went in to calculate how big would the gravitational wave phase shift be for a population of binaries that will form just in standard clusters. And this here is some of the results that we found. So this here is the peak frequency of my gravitational wave source that I'm forming through the triple scattering. And this up here is the phase shift. And the different colors are for different semi-major axes of my binary black hole. Okay, and what you see here is so every time, so if you're above 10 to the minus 2, 10 to the minus 1, if you're above this limit here, you're definitely going to see it with Einstein telescope, definitely. Okay, so we have been estimating, so probably about 5% of all the sources, or 5 to 10% of the sources will show these very high phase shifts, right? And you can easily see them with the Einstein telescope. So this is, so then I just want to explain here that if you just do a first order calculation and calculate how big should the phase shift be, if I just restrict myself to a binary system with a characteristic semi-major axis and an object coming in here, I would not be able to generate phase shift above a certain limit here. But we do see a lot of sources that have huge phase shifts that we can easily see with the Einstein telescope. And they are coming from the, that is 3 different semi-major axes for my binary black holes. And sorry, it's not written on this one here, 10 to the minus 2, 10 to the minus 1, and 1 AU separation. So what is generating these highly eccentric and also high phase shift sources is just the chaotic triple problem. So sometimes the binary just happens to be very, very close to a single when it's merging, right? And we can calculate this fraction, and it's a well-defined fraction, right? And many of the systems that you'll end up with are these where you have a binary that's very close to another object, right? So you can also apply your lensing methods and so forth on these systems. Right, so then I'll come to the last part here, which is actually the title of my talk, but now, but it's just, it's some calculations that I did recently. It's just multiplying a few lines, and it's basically just tapping into what I already told you about with these phase shifts here, right? So I was thinking about, well, what if we don't have a curved trajectory? If we have one observer looking at, different parts of this curved trajectory, like what if we have, we have one observer, we don't have a curved trajectory, but we just have a linear motion. And instead of having just one sightline, what if we could have 2 sightlines towards this one here? This is basically what it's showing. Showing a strong lensing event, right? You would have 2 sightlines towards our binary black holes. And if the binary black hole is moving from here to here, it will basically be blue shifted along this sideline relative to this one here, okay? And I could go in and calculate this blue and like the differential blue and redshift. Okay. And that one is 2 pi tau over t, with t, tau is the time displacement. And the time displacement is this phase shift that I was talking about earlier. And this tau, the displacement here, is essentially just coming from a differential, like a differential or a difference in the radial velocity along the line of sight when the source is moving here, right? Because when it's moving, so if the opening angle is theta here, and I project the velocity here along the line of sight, I will have 2 components, one going in this direction and one going in this direction. That gives rise to the differential Doppler shift. And that's what I call delta V here, and that's proportional to the transverse velocity times the opening angle of my lens system here, divided by the speed of light here. So I can go in and calculate essentially what is my phase shift that I expect to pick up as a function of, well, in this case, an expanding universe, right? So I have an effective velocity, Vd, which is not just the velocity of the source, but it's a combination of my source, lens, and observer. Yeah? Well, it is because that, like, every time, so this is true for any strong lens system if things are moving relative to each other, right? So if you have a strong lens system here and you have a source and you're sitting as an observer down here, then if you have 2 images and the source here, say, is moving like this, right? Then it looks like this source here is being blue shifted like along this line of sight relative to this one here. This here will be redshifted, here will be blue shifted. You can do a simple calculation showing that the projection vector, like the V, okay, so this is V transverse. If I calculate what is the V along this axis here from this sightline here, this projection, so I project it down here, and this opening is theta. This part here is V transverse theta, and this one here will have another one that's pointing in this direction. That will be V transverse theta. So the total differential redshift will be VT 2VT theta. That is true for any strong lens system. I found an old paper that was looking at this for light in the late 80s, and it's very, very different to do with emission lines, just because that you don't have a you don't have a coherent signal. Like when you just look at photons, then you just have like an emission line that has natural broadening. The point is here that as a function of time t, observational time t, I can build up the phase shift. But of course, the frequency and the time is correlated with each other if I also assume that the binary black hole is merging during my observation time. Very simple to put in. If I just have a source here with emergent time t, I can express this as a function of the frequency. I can put this into my equation here. I put in characteristic values for whatever we are looking at here, and I can find here then the displacement will be of order 5 radians for an opening angle of 25 arc seconds, masses of order solar masses, hertz, and a relative velocity of 1,000 kilometers an hour a second. Right? That is yes. Well, so here I do hope to see maybe something for galaxy clusters. I believe that people have seen strong lens systems up to several arc seconds, right? Is that true? 50 or like maybe up to 50 even arc seconds. So we did a signal to a noise on this. I just have one more figure here. Over here, so this is just one example. So if you have the source, the binary black hole source redshift here, and then you have the total mass of your source here, and you choose your velocity, the relative one is 1,500 kilometers a second, with an amplification factor of 10 in the images, then you can easily measure this effect here with the delta signal to noise of 8 in this region here. Of course, it goes up here. So this is for Einstein telescope. And so, of course, it depends a little bit on what is the distribution, like especially sensitive to the mass of your binary black hole. But this is an effect that if the source and lens and observer are moving relative to each other, it should be something that you should be able to see in any strong lens system of gravitational wave sources. So the next problem now I'm trying to figure out is what is the characteristic relative transverse velocity of the different, source, lens, and so forth. And from the astrophysical side, you can ask the question, what is the most likely transverse host that you can have depending on your gravitational wave source? If you're thinking about old elliptical galaxies, they will probably be in the center of your galactic clusters. They will not be moving much. But if the binary black holes is formed through, gas-rich, galaxies that are going through gas shocks, are going through filaments and so forth, then the flow, the transverse flow, will be very, very different from these. Transverse flow is very, very difficult to measure. You do it with CMB. You can do something with the CMB, but otherwise, this might be only like some of the only ways that you can measure the transverse flow of your gravitational wave sources. Okay, thank you.